Welcome to the second part of Alibaba Quantum Summit. Today we will have 4 speakers. The first speaker will be Professor Bei Zhen from University of Guelph. Let's welcome.
Thank you, Zhengfeng. I actually was your chair yesterday. Yeah. Okay. So, for those of you who actually know me, my talk title is a title of a series of conferences I'm co-organizing, and we had the first one last year in Shanghai, and the second one we had this year in Zhangjiajie, and we're going to have the next one January next year in Harbin. So we're going to start from the idea of IT from bit, which sounds like pretty trivial. Okay, I need to change the slides, thank you. Yeah, because I don't have the remote, I do apologize for that. I'm actually kidding, it's not IT, it is it from bit. That is the idea from a physicist, John Wheeler, dated back to the early 90s. The idea is, for whatever it is, an atom, a spin, an electron spin, or a field, all things physical must have some fundamental explanation. And in short, that all things physical are information theoretical in origin. That means everything you should need a theory that building up on bit. Actually, earlier this year, when we sent out the invitation, Chen sent out the invitation for our second conference, we called the conference, the second conference on quantum matter, information, and gravity. Charlie Burnett replied to us, accepting the invitation to the conference, and he said, the timeline and importance of the topic shows even in the conference subtly redundant title. The scientific community is in the midst of an unfolding realization that there is no other kind of matter, information, or gravity. That means everything is intrinsically quantum. So that actually challenges the idea of it from bit, because everything should be intrinsically quantum. Professor Xiaogang Wen, actually in 2014, he had a blog saying that, proposing that it's from qubit, not bit. And he also mentioned that we live inside a qubit world. 我们生活在一个量子计算机里. So we live in a quantum computer. So naturally, the idea of it from qubit, meaning that we should have the fundamental theory of quantum, of the world, from the quantum theory, that is the qubit. So nowadays, it from qubit is famous from this Simon's collaboration on quantum fields, gravity, and information. Many of you actually learned it from there. So, as we already mentioned, it from bit has 3 main ingredients: matter, information, and gravity. The idea is those are all related fields and should be intimately connected to each other. So let's start to talk about matter. We know that the Nobel Prize last year in physics was awarded to 3 physicists for their theoretical discoveries of topological transitions and the topological phase of matter. So that is a new kind of matter that is so exotic, and we need theory to understand them. Later this year, the Berkeley Prize for Condensed Matter Physics was awarded to Professor Alex Kitaev and Xiaogang Wen for their series of topological order and its consequences in the broad range of physical systems. In fact, that is also the theory leading to the topological quantum computing. And what is interesting is very recently, the 2016 Dirac Medal and Prize was awarded to Charlie Burnett, David Deutsch, and Peter Shor for their pioneer work in applying the fundamental concepts of quantum mechanics to basic problems in computation, communication, thereby bringing together the fields of quantum mechanics, computer science, and information, creating the field of quantum information science. We actually noted that the Dirac Medal is the highest award to theoretical physics. So we really do not distinguish anymore if you're a computer scientist, you're a mathematician, or you are a physicist. We all together on this quantum information science business, which is also theoretical physics. And the Simons collaboration actually brought out a huge number of fields together, such as string theory, ADS-CFT correspondence, black holes, tensor networks, information scrambling, spin networks, holographic duality, quantum chaos, topological orders, out-of-time order correlator, holographical entanglement entropy, and quantum error correcting codes, or many, many others. Those things, first of all, those are all fancy words. But the main thing is they have so much connection deeply. So this Simons collaboration will bring them together. And the underlying thing is we are going to understand the theory of gravity deeply from the understanding of how qubits play with each other. In this field, so I put some random faces there. You might recognize some of them. Professor Joan Matasina, that is famous for the ADS-CFT correspondence. This is our good friend, John Preskill and Patrick Hayden. So they are actually one of the pioneers of this collaboration and started work on this many years ago. And also we're proud of our fellow Tsinghua alumni, Professor Xiaoliang Ji and Xi Dong made significant contribution to this field. Okay, so we're having a very fancy world of information, matter, and gravity, and we want to understand them fundamentally from qubits. The recent theoretical developments are very exciting. However, the problems, there's no way we're going to do experiments to actually verify the theory. However, we have something else. We know that if you could not make something, the best way to do is to fake it. So that is what Richard Feynman told us, that we can actually simulate the fancy quantum world with a quantum mechanical computer. This is what brings us here, right? And we're trying to make such a quantum computer. So during the past 20 years, theories made a significant contribution to how we're going to do quantum simulations. Famous ideas including that the quantum circuit model we're using daily, and which can run, for instance, the quantum Fourier transform. And for quantum simulation of physics evolutions, we know we can decompose the complicated Hamiltonians using the Chorley expansion. And we know that our system has errors, it's quite fragile. But we have the idea of quantum error correction, or we could compute topologically. It seems like theoretically we solve the problem. We're going to build a quantum computer to simulate the world. Because we're living inside a quantum computer, as Professor Wen mentioned, we should be able to eventually understand the theory of everything from qubit. However, the problem is, how do we actually get there in reality, not just in theory? So 20 years ago, after the discovery in 1995 of both Einstein condensate and the theory of fault-tolerant quantum computing, Professor Szegedy and his colleague wrote a paper to Physics World that recent experiments have deepened our insight into the wonderful counterintuitive quantum theory. But are they really harbingers of quantum computing? We doubt it. So the theme of the discussion, which was 21 years ago, and Professor Harold actually got a Nobel Prize for his efforts in realizing quantum information precision. However, his advice, even today, remains vivid, and the conclusion is pretty like the large-scale quantum computer, though it may be the computer science dream, it is a good dream, is the experimenter's nightmare. There are physicists in the audience. Many of you guys are experimentalists. You know what I'm talking about. It is our nightmare. It's too much. So we've never into that physical regime. We don't know how to operate in these things. That's too much for us. So the idea is, although we don't get there immediately, we decide, also as Professor Harold suggested in this paper, we should really start from very, very small things. So what he's suggesting that even if quantum computing remains a dream, the physics of quantum information precision at the level of a few qubits remains fascinating. That was what we were doing for the past 20 years. We made a lot of progress in understanding those physical systems. Now we're very excited for, at this moment, after the 20 years of hard work, near-term devices now into the 10 plus qubit regime. And with some hope, we could possibly go into a couple of times more in the next 5 or maybe 10 years. This already makes us very exciting because we will never go into even that regime. So for the past 20 years, we're in the regime of like 5 qubits. Now we can do 10. We'll never operate in them. We don't know what's going to happen there, but there's a lot for us to learn. It seems that we're still very far from our dream for building a large-scale quantum computer. However, physicists are famous for being very, very persistent. It took LIGO 40 years to finally detect gravitational waves, and those 3 guys just won the Nobel Prize this year. So it's only 20 years for us. Will be very, very, it's very, very promising for us if we are already in the middle of our journey. In fact, we'll be very thrilled. Is that the truth? There's only 20 more years to go. So, having said that, what I'm going to tell you next is we're really going to put it on a small stuff and to show you how we're going to simulate the it from qubit ideas on a real quantum computer, although it is very small, as I have just told you. So, let's get started from our favorite system, the IQC NMR Nuclear Magnetic Resonance Quantum Simulator, with our favorite people, David in the audience, and our favorite system, the 12-qubit system, that's carbon-13 labeled 12-qubit system, with our favorite Hamiltonian, which is this one. Well, we have the Z term and the ZZ coupling term with the coefficients you can find in this table. Okay? So our goal is to simulate physics evolution. And what we're going to do is, okay, this is the M Hamiltonian we're going to simulate. And this is our internal Hamiltonian with the parameters. And those are the control fields we can apply to the system. And the goal is to simulate the evolution of the entire system from controlling the field by the Shor expansion. Okay, this seems like the standard theory, but by even looking at what are the numbers here and what I'm writing here, you know this is gonna not be easy. In order to overcome the hard problem of controlling the system, techniques are developed. One of the famous one is the so-called grape. It's quite delicious. Gradient ascent pulse engineering proposed in 2005. So it's an optimization algorithm which we use to do our quantum control. We practiced it in 3 qubits, 4 qubits, 5 qubits, 7 qubit systems, and we achieved very good results. However, obviously, this method is not scalable, and it's extremely sensitive to the small errors on our model. Also, if you really go into the 12, our favorite system of 12 qubits, we have very much trouble on it. In fact, recently, we managed to create the so-called 12-qubit coherence. That means you are going to create 12 qubits in your system by using the quantum control techniques we're developing in our favorite system. However, the experimental results you could possibly see that the grip method you could possibly use to optimize your system has very bad results, relatively bad results due to the unknown noise in your system. But based on a very smart idea proposed by Jun Lee, who is in the audience, we managed to use a quantum computer to feed back to itself and end up having better control of the system based on the quantum control. So the effort of this experiment took actually 5 years together. It's really leading by Dawei. It's pretty much the state of the art of our system we can actually gain control. So that's basically the technical developments we had in the past many years. Now, the next thing I'm going to tell you is, given the control of the system, we tried to do some baby experiments to actually simulate those fancy ideas I showed you in the beginning of the talk. Okay, so here is like a summary of all the other systems. This is a little bit old. We updated up to 2015. But what you could see here is the control we gain in our NMR system is among the very best compared to other systems. So the first story I'm going to tell you is the simulating of topological orders, the famous 11-1 topological order with a 3-qubit system. So actually, if you put the topological order system on the torus, the smallest system you can use actually only unit 3 qubits. What we did is we measured the so-called modular matrices. Those are topological invariants. That is experimental results we're showing here with very high fidelity that we were able to distinguish 3 different topological orders. One of them is Z2, that is a famous toric code, and the double Fermi model, and the double Fibonacci order. So this one is the one will lead to universal topological quantum computing. And we also implemented the first experiment on measuring the out-of-time order quantum correlator. So it is a correlation function that tells you whether your system is chaotic or not, or how chaotic it is. And also, the early time behavior of the correlator shows something related to Lyapunov exponent with upper bound 2 pi over beta that is only achievable to believe by the black holes. The experimental results, we did the experiment with a 4-qubit system, and by really doing a Shorian expansion to simulate a real Hamiltonian with Ising interaction with both the X and the Z magnetic field. In experiment, we choose the coefficients. Those are known to be theoretically known to be integrable and chaotic. From the results, you see the lines are actually the theoretical results, and the red dots are the real experimental results. So this shows very high precision and clearly shows the distinction between an integral system and chaotic systems. And recently, we did an experiment simulating the the discrete ADS correspondence proposed by John Prescott and colleagues. This is actually a time slice of the Eddy, a two-dimensional Eddy de Sitter space. And what we did is in a 6-qubit system, we created, so the ingredients of this thing is something called the perfect tensor. It's actually a very good quantum error correcting code. What we did here is we were able to create these states and mirroring its entanglement entropy, and which are consistent with this so-called Ryu-Takanagi formula for holographical entanglement entropy. And furthermore, we also studied the simulation of quantum space-time. So what you were seeing in the previous slide is actually a space slice of this thing, and you go up with your time. And the building block with this loop quantum gravity theory is something called is some kind of geometry. So we learned from Einstein that geometry is gravity. So the geometry has a building block, a tetrahedron, and with the flow which has to be conserved. So you have the flow field has to be conserved, and mathematically it's going to correspond to something we call invariant tensor, where the system has to be invariant under the global SU2 rotation. And if you write it down, in the smallest system of 4 qubits, this is a quantum error correcting code for experts correcting strong collective decoherence. Actually, it's a decoherence-free subspace for that. But it has different geometry, depends on the coefficient. So the encoded qubit, so it's actually a 4-qubit encoding 1 logical qubit, and this shows different geometry for this tetrahedron. And the final manuscript is going to appear very soon. Okay, so we had so much fun recently simulating the wonderful idea of E from qubits in our NMR system and demonstrated very good control. So we thought about it, okay, this is so much fun, we should actually share with you guys. So we decided to put our system on cloud. So what we did is actually 2 days ago, we announced our NMR Cloud Q website. On this website, what you could possibly do is what I just showed you. So you can now simulate your whatever idea physically on our system. The first one is only in 4 qubits, but we're going to try to do more in the future. And we also had a paper on arXiv for all the technical details. And during the past 2 days, over 100 experiments have been done on our system. So I encourage you to actually try it out. Thanks. Okay, so I really should thank the team. It's a wonderful team, supported by this this is a real quantum computer operating online. This is actually, the lab is actually Tsinghua, leading by Professor Guilu Long, and I think many of you know him. So this is a collaboration supported by this IQC Tsinghua collaborating program. It's very successful, and we work together. And you actually see Tao Xin, Jun Li, Shilin Huang, and Da Wei. They are actually all here. So if we get any technical question, those are the people to ask. Actually, I speak for them. I don't do the experiment. Okay, the most importantly, I should thank everybody for being here. It's very nice to be with you. Merci. 谢谢大家。
Thank Bei for this exciting talk. Our next speaker will be Professor Qiang Zhang from USTC, telling us about recent experimental progress on quantum networks. Let's welcome.
Okay, thank you for Yaoyun's invitation. And yeah, I'm very glad to be here. Today I will talk about the recent experimental side, hardware side, in the quantum network. I'm from USTC, exactly from Quantum Physics Quantum Information Center. But anyway, we also known by the Jianwei Pan group. So we have the quantum communication. It has actually many branches. We have the quantum cryptography. We have the quantum key distribution, the quantum money, the bit commitment, and the secret sharing. So quantum key distribution is like you use the basic principle of quantum mechanics. You exchange a key, you trust each other, and then you use the quantum key to do the classical communication. It can provide the unconditional security. And the quantum money is like the bank give you some quantum state. You bring it to some supermarket or bank, and they can verify that. You cannot forge it. For the bit commitment or the coin tossing, it's like you don't trust each other. You want to reach an agreement. And the secret sharing is just like among a group, you do the quantum communication. You reach an agreement. And if you want to implement it, you need a scalable quantum network. Here you need a quantum repeater or quantum satellite. And except for that, we have the quantum channel complexity. Like for quantum dense coding, you have the limited channel. You want to transfer more information, all the fingerprinting by Dr. Pochman. So it's like you want to implement some task, and you use kind of less quantum resource. Or data locking, you use the less key to lock more information. There exist other protocols. So today I will talk about QKD, quantum money, repeater, and satellite. For the quantum key distribution, we know nowadays we're using the classical encryption. It's based on the computational complexity. So the security we can call is computational complexity security. And we also have the quantum key distribution assisted security. You use the quantum key distribution, and it based on the quantum basic principle. You cannot clone an unknown quantum state, and the single photon you cannot separate it. In that sense, with the quantum key, and you use the one-time pad method, you can get the information theoretical security. It means like as long as you accept the information theory and you accept the quantum physics, okay, it's secure. And we have two basic methods. One is the BB-bus typed. It's kind of a prepare and measure. You use a single photon, or you use a quantum entanglement. There are two basic methods. And nowadays, people using the prepare and measure. Why we use prepare and measure? Because it's simple. It's if you want to commercialize that, you need some chip device or chip system. And here, the basic scenario for prepare and measure, you have the Alice. You have Alice is the sender, channel, and the receiver is Bob. So because you are using the realistic devices, so it may have some loopholes. People always, each time I told people that, okay, QKD can provide unconditional security. They will ask, okay, you are using some realistic device. How about the physical security? So, okay, the first problem, if you really want to push it to commercialize, you need to fix the problem with the security loophole with the realistic devices. So in the sender side, you need to prepare your qubit. So a light source may have some problems. The random number generator may have some problem. And also, for the channel, you can use fiber or free space. But for this side, the security proof is guaranteed by the security proof. And for the detection, you have a lot of detection things. So you need to care about all these kind of things. For the preparation, first the problem will be you do not have the single photon source. So you use some decoy state or other method. I'll talk about later. And also for the quantum random number generator, I remember yesterday, Bochman bring a quantum random number generator from IDQ. But that one has a loophole. I think Yaoyun has the problem with that. Yeah. Yaoyun think, I agree with that. Yeah. you need to verify that, and you need to find some way to fix that. And also the study preparation. Okay, so I think the main loophole, if we talk about some realistic device or realistic system, first of all, you need a single photon source. But single photon source is very expensive and it's very big. So if you want to use some commercialized system, you use a laser pointer attenuated to single photon level. In that sense, there will be some loophole, and you can using the photon number splitting attack to attack that. And then there are many solutions, but I think the optimal solution is the decoy state QKD. And in 2007, together with NIST, the two groups back to back, we published a 100 kilometers paper in Fiber, and also 2010, we pushed it to 200 kilometers. And from that side, I think the kind of photon number problem can be fixed. And later on the detector. Actually, detector, nowadays, the current kind of attack is based on the single photon detector. You can see there are many kinds of attacks on detector. And then there are some, for example, the very famous attack is blinding attack, which means the single photon detector is working in the Geiger mode. If you use some strong light, you can make it in the blind mode. And even stronger, you can make it in some linear mode. In that sense, you can control the detector. So for the eavesdropper, can control the detector for the receiver. So the solution is measurement device independent QKD. This one is provided in 2012 by Huakong Low in Canada. Oops. Okay. So and then we here I just talk about I don't want to talk about the detail about the technology. It's also like in 2013, we did the first proof of principle demonstration in the lab, and then 2014 we pushed it to 200 kilometers, and 2015 is field and also network test in Hefei. And nowadays the current result is about 400 kilometers. I remember yesterday Stephanie pushed it, mentioned the world record is about 300 kilometers. Yeah, I just told her to update her PPT, because now the record is about 404 kilometer low loss fiber by our group in the lab. Anyway, it's but at 100 kilometers the carry is about 3 kbps. In that sense, you can do the kind of telephone, and you can do one-time pad encoding for a telephone. Yeah, that's the current status for the MDI QKD. When you finish all these kind of things in the lab, and then you can think about the implementation in the field. Okay. Later, I'll talk about the quantum money. The second protocol is quantum money. The original quantum money protocol is provided by Wisner in 1970. It's actually the first quantum communication protocol. Unfortunately, his paper was rejected. And then eventually he published in 1983. And this one is still earlier than the BB84. So, but later on, people found it's vulnerable to the adaptive attack. In that sense, the new protocol is provided by so there are many kinds of new protocols. We picked the one by the Amiri and Arzula. They are published in 2017 in PRA. The basic idea is like you have the bank note, like you have a bank, and the bank, for the bank, they has a lot of random numbers, and then they just using, and then they use the very coherent state. Meaning they using laser point, they use a laser, they attenuate it to a single photon level, and then they just divided the laser pulse into many groups, and each group probably it has about 4 pulse. And in the group, the 4 pulse, they are all phase correlate, they are all phase coherent. Means like, and then the bank, they can encode the pulse, like using 0 or pi. And you can see this x1, x2, x3, x4. And then the bank will give to the user, to the customer, for example, for the customer. And the customer they will give the customer a chip or quantum money, whatever it is. And the customer, when they want to use the quantum money, they just put the note, the bank note, to the bank or to the supermarket, and then they will do the verification. The verification procedure is simple. The bank, they will randomly choose any two of the 4 groups to do the interference. For example, for pulse, you have about 3 kinds of matchup method, and you can do the 1 4 and 2 3, or 1 2 3 4, or 1 3 2 4. For just randomly choose one, and then they will do the interference. They get a result, and to check whether it's similar to the previous preparation. If the same, okay, it's not forged by the customer. And here is our experiment. We're just using the laser pointer, intensity modulator, phase modulator, attenuator, and then do the verification is under. We use some fiber Mach-Zehnder interferometer. In this sense, the whole setup you can minimize into a chip in the future. I think the probability is about 10 to minus 7, the forging probability. And actually, there are 2 papers, except for one paper is from our group. You can see the first one. And second paper is from French, Eleni Diamantis group. It's put on the archive almost at the same time. And the future will put a quantum memory, and also it's not portable. In the future, probably we would like to put it in chips if it's really interesting for the users. Anyway, I think Zhengfeng may have some good idea about this one. Okay, so now talk about some implementation in the network. We have many kinds of quantum network. We have the Europe network, the DARPA network, Tokyo network, and also the Switzerland network. And I'll talk about our network. This one is a Hefei intra-city quantum network. We do a lot of things on the network. We do teleportation. We do the QKD on the network. And you can see this is the device on the. This is the device on the network. This is the quantum kind of sender and receiver. Alice or Bob are in the machine, and you can see that there are some products. And we have the Jinan quantum communication networks. We have about 56 nodes, and this one is still running. And everyone, if you are interested, you can using this network to do QKD protocol or test your device. One thing I should mention is because it's a network, so it's not point-to-point link. Not everyone is Alice or Bob. For example, let's say in the Jinan network, we have some kind of relay station. Not all the users are either the same. Not all the users they have the sender or the receiver. For some node, they are kind of a metropolitan node. For some node, they are just the access network. For example, for this kind of small users, they just sending they have only a laser. They have only the quantum sender. They didn't have the receiver. They exchange key with the relay station, and you need to make sure the relay station is secure. It's just you need to trust the relay, and the relay, this relay and this relay, they can do the quantum key distribution between them, and then this station exchange the quantum key with this relay. In that sense, these 2 stations can make the key exchange through this kind of trustable relay system. And for all these protocols I have mentioned here, they are using the decoy state method. We didn't use MDI yet because MDI is just developed very recently. And in the future, we are thinking to change the central relay station by MDI QKD setup. And then the relay is very simple. It's for example, the Alice will exchange his key with the relay. Bob exchange his key with relay. And relay is just for the relay, just do the XOR and announce the XOR result. And then Alice and Bob, they will share the quantum key. This one is not perfect because you need to trust the relay. But MDI is better. MDI, you need not trust the relay. But I think for the metropolitan area, eventually we probably do not need a relay. Maybe only for the access networks, small station. But for the long distance, since the photon is absorbed by the fiber, the visibility also reduced. So the solution will be there are several solutions for long distance. The first one is maybe a little bit trivial, using the quantum backbone line. It's just actually opened in the end of last month. And here you can see it's the quantum backbone line. Its total length about 2,000 kilometers. You have 32 trustable relay nodes, 31 fiber links. you have 4 metropolitan networks, Hefei, Jinan, Beijing, and Shanghai. And for all these 4 networks, they have users in all these 4 networks. And for example, if there is other city, for example, Tianjin, they want to get access to the network, they just build a metropolitan network and then they can connect it to this one. You can think it's like the high-speed train in China. And the metropolitan is like a subway. That's the basic idea. But for this one is, I think for now the K rate for the total line is about more than 10 kbps. And for the next years, we will do some security check. We will do the stability check and the security check. After that, we will put it, we probably will hire a company to commercialize that, to share the bandwidth, probably. But I think next year, people will test. We probably will invite a lot of hackers to hack this system, to check its security. Okay, the second solution is the quantum repeater. You have the quantum, it's based on, the basic idea is based on the quantum entanglement, quantum teleportation. You use the quantum entanglement purification or error correction. You use the entanglement swapping, and then you use the quantum memory. I think recently the quantum teleportation in the free space, we get about, except for the quantum satellite, we got about 100 kilometers in 2012. In the fiber side, just very recently, we get about fiber in the Hefei metropolitan network. We got about 100 kilometers entanglement swapping. And I think in that sense, for the metropolitan area, we can definitely do the quantum network. But the problem is there is no field test of purification. And by the way, probably the purification should be in the lab. So I think the main problem for quantum repeater is the quantum memory. You do not have very good quantum memory. I think that's the very difficult part for quantum repeater. And yesterday, Stephanie mentioned about their kind of a project for the quantum internet. I think even in I think our group also shared the same kind of project. Probably in 2020, we get a kind of, they are thinking building a kind of metropolitan things. We are thinking to build a kind of a backbone line, but 500 kilometers, quantum memory assisted quantum repeater. But for that one, we couldn't do the purification. It's just like entanglement swapping. And then you connect, you distribute the entanglement by 2 quantum memory. And in that sense, 500 kilometers, probably you get about one bit per second in that sense. But I think we still need to take time. But you cannot tell what the technology will come. Because I think 5 years ago, no people think 100 qubit is possible. But so I think quantum repeater, we will see. We do not know which, they're still not decided which system will be the optimal candidate for quantum repeater. Maybe the cold atom ensemble, the solid state. I don't know, the color center. Let's see. Yeah. That's a very exciting field in research, I think, in the next 10 years. And for the third solution, the solution is the quantum satellite. Maybe you all know that. It's launched last year, August. And yeah, it's 500 kilometers orbit. And this is some picture. And actually, it's we have about 5 stations in China, and now we have 1 station in Austria, and in the future probably in Italy, Canada. I'm not quite sure. Japan, we may have several stations. You can do the quantum K distribution. You do entanglement distribution. Entanglement distribution basically inside of China. QKD you can do the continental. Actually, we did a continental QKD in the end of last month. We use quantum satellite and also the backbone together to do a QKD. And Anton Zeilinger can make a phone call with our president for CES. Anyway, but anyway, for the satellite, it will pass the ground station per 8 minutes per day. So you have only 8 minutes to get K. Yeah, sorry for that. And here you can get some picture. And the green light is the satellite want to settle some backlight from the satellite to the ground. And the red light is from the the station to the satellite, or a backlight. I'm not very involved in this project, so I just introduce their work. Yeah. Here is now existing quantum network in China. And in the future, we are thinking to build more kind of quantum networks in China and also more satellites. Recently, we already fixed the problem of the daytime. I mean, with the sunlight background, we can make the quantum satellite. I mean, it's just a ground test, but in the future, I think it's possible. And people may ask about the bad weather. That one may be a little bit difficult, but we are thinking about some solution. And here is our teams. Of course, I couldn't include all the peoples. And we have many fundings. And advertisement. There is QCrypt. There is the biggest quantum cryptography conference in world, 2018 in Shanghai. And you're welcome. So yeah, that's all.
So we will have a tea break. Let's resume 10:15. So 我们现在是茶歇时间，10点15分重新开始，谢谢。
各位来宾，本次会议将于5分钟后开始，请各位尽快就座，同时请将手机调到静音模式。各位来宾，本次会议将于5分钟后开始，请各位尽快就座，同时请将手机调到静音模式。 各位来宾，本次会议即将开始，请各位尽快就座，同时请将手机调到静音模式。各位来宾，本次会议即将开始，请各位尽快就座，同时请将手机调到静音模式。各位来宾。
Welcome back to the second half of the session. The next speaker will be Andris Ambainis from University of Latvia, telling us about recent developments in quantum algorithms. Let's welcome.
The right presentation, the version of presentation. Okay. So my talk will be slightly different from most of talks here. Instead of trying to give another survey of a broad area, I will talk about a few specific developments. So I have chosen two developments in quantum algorithms to which I have contributed together with my collaborators, and I will give a somewhat more detailed perspective of those two. And my main focus will be on quantum search. So search is one of the main applications for quantum computing. So I'll start with describing background and telling about the early results on quantum search. And then I will tell about one new recent result on quantum search to which I have contributed and which I find very interesting. And then after that, I will switch topics and turn to the topic of what is the maximum possible quantum speedup, what can be achieved. So here is a standard quantum search as introduced by Love Grover in 1996. We have a number of objects, and we would like to find an object with a certain property. For example, we might be looking for a certain person's name in a database. And we have n records, and these records are not ordered in any way, so the only thing that we can do is we can look at a particular record, open the black box, and see whether it's the right one or not. And on a classical computer, if there is 1 million objects and just one object with the right property, there's always a chance that it will take 1 million steps until we find the right object. And quantumly, surprisingly, this is no longer the case. If we have quantum access to these n objects, we can search them in square root of n quantum steps. So for 1 million objects, we would go from time 1 million to time 1,000. And this is applicable to a variety of settings. In popular scientific press, this is usually described as searching a phone book. We have phone book with million records, and we would like to find a person with a given phone number. So then we can do that in 1,000 steps instead of a 1 million. But the really big application of this is not searching phone books, because to search a phone book, we would need to represent the whole phone book in a quantum memory. So we would need a lot of quantum memory to store a phone book. And a phone book with 1 million records in a quantum memory will not be practical anytime soon. So the really big application is if we try to solve problems that involve searching a large amount of possibilities. For example, optimization problems where we have to find the best schedule, the best route, or best something. So for example, in traveling salesman problem, we have to find the best route through all the cities. Well, if there is 1 million candidate routes that we would like to check, then quantumly we can do that in time 1,000 instead of 1 million. And this is applicable to any problem that involves searching a large number of possibilities. Take your favorite search problem. Quantum search will be applicable to it. So here is another problem. We can think of breaking ciphers. We have somehow managed to get hold of a message, secret message. We know what it was encrypted to. We would like to find out the secret key so that we can read everything else that is encrypted with this secret key. And ciphers are usually designed so that for classical computers, there is no good method of breaking the cipher. So the best method is just to look through all the secret keys. And quantumly, even if there is such a perfect cipher that hides all the structure, we can still use quantum search to break it. And instead of looking through n keys, we have to look through just square root of them. And so quantum search has been invented almost 20 years ago, and since then it has been generalized in a number of different ways. For example, we get quantum advantage not just if we want to search among n objects, but also if we want to estimate the fraction of objects with a certain property. And then again, we can do it quadratically better than the best conventional algorithm. And there are many more complicated statistics of data that can be estimated in the same way. Okay, so now let me turn on to the new development, which is quantum speedups for smarter search strategies. So Grover's search provides quantum advantage over a very naive conventional search algorithm that searches all data one record by one record. And in practice, classical computers often use more complicated search strategies. So for example, here is a strategy that is called backtracking. We start with a partial solution to the problem, and then we try to extend this solution. And if at some point we get stuck and we realize that this doesn't work, we step one step back and try something else. And if that doesn't work, we step even further back and try something else. And backtracking is commonly used for a lot of different things. It's used for SAT solvers, it's used for optimization, it's used for many applications. And it's something that is more difficult to speed up using quantum computing than naive search. And the reason is that this process, it has some inherent sequential nature. It searches through these branches in a certain order, and we only get to a certain branch after we have searched other branches. In naive search, where you're picking through n possibilities, you can go through these n possibilities in any order. Here there is some order which you learn as you are searching. And so here is an example problem that you can solve with backtracking. Let's say that you have this graph, a sequence of dots connected by lines, and you want to color vertices into 3 colors so that for each line, its endpoints are in different colors. So you can do it easily with these 8 vertices, but in general, this is a difficult computational task. And then there is a easy strategy how we solve it classically by searching all possibilities. We try to color vertices one by one. We color first vertex, then we try to color second vertex in whatever color possible, then we try to color third vertex, and then we get a tree of possibilities like this. The top is the situation where no vertices have been colored. Then the 3 vertices on the next level are 3 ways to color the first vertex. The next layer is ways to color 2 vertices without getting into trouble. The next layer is ways to color 3 vertices, again, without violating the constraints that we have. And then we get a tree of possibilities. And the then if we manage to color all the vertices, that's the solution that we have been looking for. And now the question is, can we find this solution in this tree using quantum search? And it turns out that the standard quantum search doesn't work, because the standard quantum search, it has these n boxes into which we look. And for standard quantum search, we have to know where is the box number I. And this tree is usually very irregular. We don't know where the possibility number I is unless we have explored the whole tree and mapped the structure for the whole tree. So here is a problem that is solved classically by searching all the possibilities, but the standard quantum search doesn't work for it. And 2 years ago, Ashley Montanaro invented a quantum algorithm that solves this problem. So it searches search trees like this in time that is roughly square root of the size of the tree. And that achieves quantum speed up over any search method of the form that I described, which searches possibilities by going forward and going back. And so here is a quick description of how this algorithm works on 4 slides on a very informal level. So it's a quantum algorithm that walks on this tree. It has a state space that consists of with basis states that correspond to vertices of this tree, and then it alternates between applying 2 transformations. At first step, it groups together vertices like this. So vertex at the first level together with vertices below it, vertex at the third level together with all vertices below, and so on. And then it applies a transformation to each of these groups of vertices. And then at the next step, it does the same thing, except that it groups vertices in a different way. Previously, you had these groups of vertices starting at level 1, 3, 5, and then every odd level. And now you have vertices grouped according to even levels, 2, 4, and so on. And then again, you apply some transformation on each of these groups of vertices. And if you have an end vertex, then you apply a transformation that depends on whether this end vertex is a solution or not. And then you can set up this process so that you start it at the root of this tree. And if there is a vertex that corresponds to solution, then there is a state that is close to this starting state that stays unchanged by this process. And if there is no solution, then there is no such state that stays unchanged. And then you can run this process for some time, and you can check whether it's still in the same state or not. And if it is, then probably somewhere in this tree there is a solution to your computational problem. And yeah, so one thing why I find this algorithm interesting is that it's actually a quantum algorithm with pretty small memory requirements. All that you have to store is one vertex in this tree. So if this tree has n vertices, then you can store it in log n qubits. So a tree of 1 million vertices can be stored with just 20 qubits. So I think this would make an interesting experiment on a small-scale quantum computer that might be available soon. And so here is another situation in which we can apply the same ideas. So let's say that we are thinking of finding the best move in a 2-player game. And then what we have to do is we have to search through a large number of possibilities. And again, these possibilities can be arranged into 3. So the root of the tree is the position at which we are. Then the next layer are positions at which we can get in one move. The next layer is positions where we can get it 2 moves, and so on. And we have this huge position tree corresponding of possible positions. And we want to determine the best move from this position tree. And then we can define a logic formula that corresponds to whether there is a move which makes the first player win or not. And to do that, we introduce logic operations at each node, and these logic operations are and or, depending on whether it's a move for one player or a move for another player. And then, essentially, evaluating who wins means evaluating a very huge logic formula that is defined only implicitly. So we don't know what this position tree looks like. We can only find it out if we explore. And then we have this huge logic formula, and we have to evaluate it somehow. And what is important is, well, we don't know this position tree. It's pretty irregular. Some branches may stop earlier than other branches. If you make a bad move, then after this move you discover that you lost. In some other branches you might go on for very long. And in quantum computing, evaluating logic formulas by quantum algorithms has been studied for a while, but typically these algorithms assume that the structure of this logic formula is known, and the only thing that you don't know is the input variables to this logic formula. And here we don't know the formula itself. Okay, so what we have discovered is that we can evaluate logic formulas by quantum algorithm faster than on a conventional computer, even if we don't know the structure of the formula. So we can use quantum computers to search through position trees in two-player games faster than classically. Okay, so now let me switch the topics and turn to another result that we recently obtained. And the topic is, what is the maximum possible quantum speedup? So let's say that we want to achieve quantum speedup which is as huge as possible, possibly on a quite artificial formula. So first we need to decide what model we use. And for questions like this, one typically tries to answer them in the query model. So in the query model, we have input to a computational problem given by a black box. We want to compute some function of this input, and we want to do it by querying the black box as few times as possible. And this is an interesting setting for quantum computing because one can cast quite a few quantum algorithms in this black box framework. For example, standard quantum search is a black box algorithm in which we have objects accessible via black box, and the task is just to find an object that is one. And classically, you can think of algorithms of this type in this form. You take a variable, you query it, then depending on the result of the query, you make another query, and so on. So you get this tree consisting of queries that you make. And quantumly, it's a bit more difficult to describe. There is no longer a tree. Rather, instead of tree, you apply quantum transformations at every step. But as I said, quite a few quantum algorithms can be cast in this form. And this ranges from search to evaluating logic formulas. These are the two things that I already mentioned in this talk, to many other things. And even Shor's factoring algorithm has a quantum part that can be described in the query framework. So the question that we can ask is, we know quantum algorithms are extremely fast. So let's say that we have quantum problem that can be solved with just one quantum step. So how many queries could that take classically? Well, we know classical algorithms would be much slower. The question is how much. And there is something that has been known about this problem already. At the heart of Shor's factoring algorithms, there is this black box problem in which you are given a sequence that is accessible through queries, and this sequence is periodic, and you want to find the period. And as Peter Shor showed, you can do that with one query quantumly, assuming that you have some constraints on sequence and period of this sequence. And if you want to solve the same instances of this problem classically, then you need a number of queries that is the fourth root of the length of the sequence. And the fourth root comes from two things. First of all, if you make T queries by classical algorithm, you can actually test T squared possible periods. And then second, there is constraint on how large period can be for quantum algorithm to work. So if you put all these things together, then you see that the same instances of finding period that are solvable with one quantum query require fourth root of n queries classically, where n is the size of your input data. So the question is, can one produce an even larger quantum advantage, something that is doable in one quantum step, but requires even more classical steps? And we invented such a problem. It requires one query quantumly. It has input data of size n, and it requires almost square root of n queries classically. And we can show that this is actually almost optimal. Anything that is doable in one quantum query is simulatable in square root of n queries classically. So now I think there are two remarkable things about this result. The first remarkable thing is that quantum advantage here can be unlimited. It's not just that you need, say, 1 million steps to simulate one quantum step. It's that the number of quantum steps that you need to simulate, the number of classical steps that you need to simulate one quantum step grows with your input data, and it grows to infinity. So if you have input data that is large enough, you will need more than 1,000 steps. You take even longer input data, you need more than 10,000 classical steps, more than 1 million, and so on. And the second remarkable thing is, okay, if you accept this idea that you will need more and more steps to simulate a quantum algorithm, then the next natural guess is that to simulate one quantum query, you might have to look at all the data. So you might need n steps. And that's not the case. You can do with a number of steps that is substantially less than the whole data. Okay, yes, and so now I will very quickly say what this task is. So the task is a bit technical. So your input data consists of two vectors, and the task is to determine whether the first vector is highly correlated with the Fourier transform of the second vector. And this, and this can be done quantumly by a very simple quantum algorithm that generates these quantum states that correspond to these two vectors and applies Fourier transform to one of them. And then it does some quantum test to see if the two results are close or not. And then we can show that even though this takes only one query, quantumly it takes almost square root of n queries classically. Okay, so now to conclude, so here is the summary of what I had in this talk. So there are two things that I covered. The first was search. Search is one of three big applications for quantum computing, along with quantum simulation and breaking ciphers based on factoring. And the big question about quantum search is we can easily speed up naive classical search. The question is what types of smarter search can we speed up quantumly? And in this talk we showed that we can speed up search algorithms that deal with trees of irregular structure. But the big question is broader than this. There are many more types of classical search that are smarter than naive search. And if we can speed them up, that would be more quantum advantage for more problems. And then in the second part, I looked at the question, how many classical steps do we need to simulate one quantum step in the query model? So the immediate open question is here, how many steps do we need to simulate 2 or 3 quantum steps? And we actually don't know answer for that. And then the next question, which is broader and more philosophical, is, okay, we know that some problems allow huge quantum speedups. Can we characterize them in some way? Can we say what are the properties of the problem that enable these big quantum speedups? Okay, thanks.
Thanks, Andris, for the nice talk. Our next speaker is Mario Szegedy from University of Rutgers. I guess the title is a bit interesting. Can you shoot? Oh, yeah. So, honey, I blew up the bit. Let's welcome.
Okay, so first of all, I would like to thank Yaoyun for the invitation. And I would like to thank Alibaba for bringing us scientists and technology people together with the users of like 80,000 users of this technology. And my talk is a little bit of a historical perspective of 150 years of development that has led us to this breakaway session. So there is a theory which states that if ever anybody discovers exactly what the universe is and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened. So this is from the Hitchhiker's Guide of the Galaxy, famous book. So one night, 5 days after the full moon, I looked up to the sky, and what I saw was this. And I learned from my father that when the moon is waning, it should show a C shape, not a D shape. So, like, am I on drugs or something? So what happens? So what happens, actually I was in Australia, and I figured that since I am at a different place, completely different rules apply. So let me go back to the 19th century, and in that physics, actually, physicists had the Newtonian mechanics and the Maxwell equations. And there was Boltzmann who, with his statistical mechanics, statistical physics, he tried to understand how the macroscopic phenomena arise from the microscopic. But at that time, physicists did not know that the microscopic world was completely different. So this is a scene in the movie Honey, I Blew Up the Kid. Now we know, and so they did not know. So we have to be prepared for surprises when we travel scales. Like actually, you can think of microscopic as a completely different place as macroscopic, just like Australia is different place from China. So, so when you travel scales, and that's what we are doing essentially, it's just like normal travel. Like we can ask the following: that so can we bring us something from that land? And it turns out that this scale travel, only very few things survive, kind of like averages, like we see averages from the microscopic world. So other question, like can we have full information about the microscopic world? Or can we build objects in that world? Like can we go down to the microscopic scale and operate there? So if we could, I'm sorry, the red color is really bad, then we would have nanotechnology, molecular design, or quantum technology. Well, that's our current knowledge. But let's go back to the history. So the young Max Planck, sometime in the 70s, I think, when he went to this PhD program, his advisor said that, well, in physics, almost everything is discovered. All what remains is to fill a few holes. And one of those holes was the thermal radiation. Because, like we know that every hot object, or even cold objects, radiate heat. And actually the wavelengths of these, because heat is just electromagnetic radiation, the wavelengths depends on the temperature. Actually a more detailed view of this, so the sun, the surface of the sun is 5,800 degrees. The inside of the sun is 1,000,000 degrees, but the surface of the sun is just 5,800. And so most energy is radiated in the green and yellow spectrum, and some energy is radiated in the red or infrared, and some energy is radiated in the ultraviolet spectrum. So it gives us a nice curve, this energy distribution like that, which I try to illustrate it with the lengths of these waves, like how much energy is given out in yellow, in green, and so forth. So that was the question, to find this curve. So we know, well, and already physicists knew because of the experiment of Young that, which was already in 1801, that the light pretty much behaves like water, it's waves. Actually, Newton said it was little particles, but then later they discovered it was waves. Physicists also knew that if they want to find out that curve, then they have this simple model where they have this box, and the side of the box is kind of little resonators, little oscillators, and inside the box these electromagnetic waves are going to negotiate an equilibrium. So two very, so actually a very smart guy, Rayleigh, he put all these things together and according to the knowledge of that time, and calculated the curve for the sun, or actually for any body at high temperature or low temperature. And what he got is not the right curve, but rather a curve in which the ultraviolet spectrum had infinite energy, and that's, of course, that had to be wrong, even though he was smart and his calculation was wrong. Of course, he was wrong because in the microscopic world, things behave differently from the macroscopic world. So he just missed one little point, which actually then Planck just concluded correctly, that when these little oscillators, which are atoms, give their energy to these electromagnetic waves, then they give their energy in pockets, in quanta. So they feed the wave with quanta, and these quanta are fixed quantities. So when he adjusted to that, he got the right curve. And his formula was immediately accepted. But Albert Einstein, who was famous of asking very good questions, he asked the following question. Like, what happens to the quanta when the wave swallows these quanta? And his answer was that actually the wave is the quanta itself. So but let's try to understand Einstein's answer. So again, the question was that when the pocket goes out, then like, does it go out, does it stay together as a pocket or sort of gets distributed like kind of a wave, and then it's too, like in the double slit experiment, and then it's too weak to get any impact on the screen. So the answer is, very surprisingly, that it's both. Like, it hits the screen, so it seems like it stays together, but it actually travels like a wave. So what? Well, so Taylor in 1909 has repeated the double slit experiment. Just he sent out like very, very weak light waves, just one pocket at a time. So when he sent out one pocket, then he got one white dot on the screen. And then he sent out another and another. So since one pocket created a white dot, he knew that it was the pocket stayed as a pocket until it hit the screen. But then when he repeated like 1,000 times and he read together the results, he still saw the interference pattern which he would see when he just sent a lot of quanta. So each pocket individually somehow interfered, like it traveled like a wave. So, but what does a single pocket interfere with? Well, it interferes with itself. So it travels like a wave and hits like a particle. And then this experiment was repeated with other things, not just with photons. It was repeated with electrons, or in 2012, it was even repeated with like large molecules. And again, it turns out that all these are also waves, but these kind of strange waves that are also particles at the same time. So these are quantized waves. So Feynman said that, well, this phenomenon, which is impossible to explain in the classical way, so it is very different. It's unlike you see anything in the classical world, and which has in its heart the entire quantum mechanics. But now you are asking, so what kind of wave is this? So we know that water waves are the waves of the water. The sound waves are the waves of the air. So what are quantized waves? So actually the very, very strange answer is that quantized waves are waves of possibilities. So possibilities that the light, that the photon would hit there or there or there or there, and so the possibilities are not equally probable, but some probabilities are bigger and some probabilities are smaller, and these change of possibilities give you the wave. Also, there is a phase which is kind of technical. It's very, very important because it causes the interference phenomenon. And so if you care about it, together a circle and an arrow would give you a complex number. So if mathematically the wave is a wave of complex numbers. Now, here comes the part of the story which I actually hate, which is that, so what I actually showed you, it was just before the packet hits the screen. But after it hits the screen, all of a sudden we know where that packet is. So the possibility turns into a reality, into an event, sort of. So that's what they said, but that's kind of sounds strange because nature would not behave that way, that, you know, once it's possibilities and then it's reality like later. So actually, the truth is that in reality, the world is just always remains like a wave of possibilities. And Schrödinger's equation completely describes how these probabilities in this possibility, in this probability wave evolves. So that's Schrödinger equation. But then how about like when we see that dot in the screen? So what happens then? Well, so let's look under the hood. So what really happens is that the packet meets some electron and then it gives energy to this electron and the electron is bumped up. So actually we should add also to the possibilities of like particle meet particle, and then like it becomes like another particle, or maybe it does not meet because the world is just a countless, like a set of countless possibilities, and physics is nothing but just a wave which tells which possibility is how probable. So as a matter of fact, the physicists have determined all combinations of possible events that could ever occur, and they wrote down the equation of the world. So actually it involves the electromagnetic force, strong force, the weak force, so they even the Higgs boson now, so they just wrote down this huge equation. And here comes quantum information theory. Because after all, this equation is just so complicated that there is no chance we can ever like decode it, right? So we need some, well, we scientists, we need some simplifications. And this is from Reddit, like this cartoon which was simplified by some funny guy, said that this dramatic looking cartoon is just this in the abstraction is like that on the right side. So let's simplify our world. So how can we simplify and extract the quantum nature of the world? So consider a world which has only two possibilities. Just that the world is in zero state or in one state. So this simplified world where instead of all these, like the electron here and the photon is there and so forth, so now we have this simplified world of just two possibilities. This simple world is called the quantum bit. So what is the Schrödinger equation in this simplified world? Well, the quantum bit, and since it is quantum, again, the 0 has some possibility and the 1 has some possibility, but in the next moment these possibilities are different, and what the Schrödinger equation describes is that how these probabilities change, how these amplitudes change. So we want to understand like what to extract from the real world to have like a system which faithfully models it. And so here we notice like two important things about the Schrödinger equation or the evolution of this wave function. The one is that before and after, if we look at the total area over 0 and 1 and over 0 and 1, so the total red area remains the same. So this is the conservation of energy. Another important thing is linearity. So linearity is that there is a matrix which describes, actually, if I know the two complex numbers over 0 and 1 before and after, well, there is a matrix like how I can go from before to after. Now what happens in a more complicated world when we have, like instead of just one bit, we have n qubits? Kind of it's strange how it compressed these numbers. In my slide it was like a line. In any case, so then like all the and then you have 8 possibilities. And so each gives you an amplitude. So again, so the world is nothing, but so these are the possibilities, but none of them, again, it's like the real world, none of them actually ever realizes. It's all possibilities with certain amplitudes. And so then it just goes again, like in the next time step, it just goes again some other amplitudes. The same conservation of energy and linearity applies. So actually a quantum circuit is nothing but like a brief diagram which describes how, if I start from a k qubit, how this system is gonna evolve. So a quantum circuit is nothing but kind of the Schrödinger equation of this simplified world. But if you notice, there is about this quantum circuit like one more thing, which is that like you are always operating on just like a couple of qubits, or maybe just even on just one. So here is the big thing in physics and also in computing, which is called locality. So this locality is there in classical physics, in classical computer. What is the locality in classical computers? So in classical computers, the locality is that you are always operating at a time, you are always operating on just a couple of bits. So you put from the memory, you retrieve a couple of bits and go only on them. I mean, maybe a couple of numbers. So that's locality for computing. So locality is everywhere, in physics and in computing. You can give an entire course on locality. So it's kind of harder to explain in quantum what locality means, but like if you are operating only on the third qubits, it means that amplitudes can go only like sort of flow locally, like for instance from 0, 0, 0, amplitude cannot flow to 1, 1, 1, only to, let's say, 0, 0, 1, so to some close by quantum state. Now if you have all these three things, which how you simplified, then you get the usual notion of quantum circuit. And what can you do with quantum circuit? Well, famously, you can run Shor's algorithm. So actually, here is Peter. He was my colleague at Bell Labs. He looked like this when he was my colleague. Now he looks like that. And actually, you know, he is quite similar. I mean, the colors have changed a little. But otherwise, you know, Peter is Peter. So, you know, famously, like so this algorithm source factoring, which is like you have a number x, and you simply want to find two other numbers like y and z such that x equals y times z. So that's factoring, and he designed a very, very efficient quantum circuit which does that. But is Shor's algorithm a reality? Because we had this simplified world. So recall that we simplified, we made a gross simplification of the real world. We created this quantum bit world, which is kind of the same rules, the locality, the conservation of energy, and the linearity, but it's a different world. So can we map that into our real world? So that's like physically realizing a quantum computer. But if we could do that, then it would be like it would prove that our world is very, very different from the world that we think it is. Like, then there would be no way to classically simulate our quantum world. So actually, quantum information theory is, well, it's a story, but actually it's not just a normal story, it's a drama. So it's a drama because there is an arch enemy. So the arch enemy is decoherence. So decoherence, what is decoherence? Well, so you might ask the question, like, how comes that quantum is such an overarching phenomenon, but until the 20th century, like, no one noticed that the world was quantum. How comes? And so why don't we see like quantum effects in our everyday life, or only we see this effect only very indirectly? For instance, the famous Chinese poet Di Bai, do I pronounce it correctly, in the Tang dynasty, so should be born and not born at the same time. But we know he was born, right? So we don't see this kind of superposition. So how comes? So what makes our world actually classical? So the answer is decoherence. So the decoherence, although our world is quantum, it tries to make our world classical. So there is a general tendency for quantum states to lose superpositions. Like, consider which is like on the X line, it's either here or there, and actually at both places at the same time, but in 1 nanosecond, this superposition just collapses and it's just gonna be either here or there. So Feynman, from Feynman to Zurek, people have studied this issue. Now forgive me my bad drawings, but so here is like the kind of the tale, the two brothers who like walk in the swamp, and then the wolves attack them, and then they just run away, and they just lose touch with each other. That's one thing, that's a terrible thing, they lose touch in each other. And the other bad thing is that they are just swallowed by the swamp. So this is what happens with the two peaks. They just get like a little less peaked, but what much worse is that they also, this superposition just disappears. It's called decoherence. So we might ask, so what survives then to the macroscopic scale? So in the microscopic scale, we see this superposition. In the macroscopic scale, if we look at from afar, we just see kind of a word line which we should see classically. So a quantum computer would be a device which would keep that superposition for some time when it is turned on. So that's what we are trying to do, like we are trying to force nature to something which it usually does not do. So how can we force it? There are we have three weapons. We have three magic weapons: cooling, quantum error correcting codes, and topological protection. And we have heard about these a little bit. So let me summarize. So quantum information theory abstracts out the wave function itself, that the world is a set of excluding possibilities. None of them happens, but all happen just a little bit. And in our abstraction, which is quantum information theory, we preserve three properties: conservation of energy, locality, and linearity. So what can we do with quantum information theory? Well, it gives a simple model of the quantum world. It is a framework to design quantum algorithms. It is a playground in which decoherence can be investigated. It is our preferred language for quantum cryptography. It is a didactical tool to teach quantum. Actually, I did not know quantum before I understood quantum information theory, and that's just so much easier to learn quantum information theory because it's a simpler world. It's a new kind of information theory which has already greatly affected the old information theory by providing novel insights into old problems. And finally, it's a fantastic opportunity to travel magnitudes down to a different world. Thank you very much.
Thanks, Mero, for the stimulating talk. Don't leave. We will have a panel discussion. I guess 8 speakers will be on the stage, and Yao-Yun will in charge of this event.
Thank you, Jennifer. I have my microphone already. Is this your first time giving this talk?
Yes.
Wow. Thank you so much. You are such a good illustrator.
Well, yeah, it's actually easier than Thailand to
Easier than...
find things on the internet.
Wow.
It's more flexibility.
Fantastic. I just sent you guys a list of questions. You can take a quick look, get some ideas. I email you guys. I just email you guys a list of questions. You can cheat, but. All right. So I want to invite the 8 speakers to be on the stage. Yeah, you can hold a microphone if your seat is there for the time being. So I had before Mario's talk, I was thinking that when I was on stage, I wanted to say, here comes the part of this workshop that is of the most fun. But after his talk, I can only say, all right, here comes the part that's of the second fun, because it's such fun to be in his talk. All right, so we have about 45 minutes. So here's a plan for the 45 minutes. I have 4 questions, or 4 sets of questions for our 8 distinguished speakers. And hopefully, there's still some time left for the audience to ask them questions. Okay. All right, the first one. So I'm going to ask our scientists to try to be brief. At the same time, if you're very passionate about a question, just raise your hand and be the first to answer. I may not ask everybody to give your opinion on every question. We are in Alibaba conference. It's not going to be, so the program I'm running is not going to be a university program. In the end, customer number 1, right? Customers are number 1. We want to provide services to our customers, applications. What do you think would be the first real-world application of quantum computing, and when is that going to happen? 大面。
So I think one of the first applications is simulating a quantum system. This is a natural task for a quantum computer because it works exactly like our quantum system. And there has been a lot of progress in recent years. So I think one of the first applications is solving some toy problem which we couldn't solve before, which might give us better insights on how to design, for example, better materials. We won't solve it right away, but we will solve some small toy problems which help us understand quantum mechanics better.
When is it going to happen? At what time is it going to happen?
We can get that done before 5 years. I mean, if you look at what a supercomputer can solve, that's on the order of, probably like 70 qubit systems would already be more powerful. We can already embed small problems in there. So I think in the next 5 years, we might be able to solve something.
Excellent. So 5 years. Anybody who wants to beat that 5 years?
No, because I talked about quantum simulation already. Practically, it's very, very hard. You saw the NMR system, but I'm telling you that if you run this on any other system, you'll find it very, very bad for now. But I do share the perspective that we do have the application of quantum simulation because we have some other very good quantum simulators. One of them, for example, is a cold atom system. So for those systems, we don't have universal control, but we have very large systems, and we can simulate some toy problem, as you said, like the condensed matter physicist or material scientist is going to be interesting, and I think it's going to happen. It's actually happening right now.
Great.
Maybe I can say something
Harry.
because I'm actually a little bit less optimistic. Sorry. But I think it's going to be extremely difficult to come up with a problem. I mean, maybe not to come up with, but to have a quantum computer that beats a classical computer at a toy problem, which would be of practical interest because the classical computers are damn good. And we have to beat them, and that's not going to be easy. I'm not saying it's impossible, but I think maybe 5 years is a little bit too optimistic. It could take a little bit longer than that.
Because one strategy is to convince people who are working on classical computers, switch them to doing quantum computer, and they would slow down the improvement of classical computer and help quantum computer. Yeah. Okay, great. Right, Zhengfeng.
I guess you asked the question of applications, and the most of the applications that we have for quantum computers are like simulating quantum systems, drugs, and these are like scenarios that are for big companies. We don't have a scenario for our customer, end users, or common people. I guess that's an interesting direction that we should look at and find for companies. These are like really important areas that we should look at.
Excellent point. Okay.
I kind of agree with Spei, because I think for some cold atoms, the simulation things, I think they already did something that the classical computer, it's, I don't think, but of course they didn't ask the classical computer to simulate that. That seems very difficult. But of course, that questions are not very kind of universal and probably not very broadly interested in that sense. But of course, if you're asking how about the photosynthesis, this kind of not that big question. So for some small question, for some exact new phenomenon in physics, I think they're happening. It's happening, but yeah, but no big question yet. So 5 or 10, I don't know. I don't think it's good time to do the prediction. It's really hard. Yeah, it's really hard. Yeah.
Well, okay, I guess one could make prediction by attaching a probability. So with 80% of chance, 5 years, and that would make it safer. Okay. Right. Any more to add, or shall I move on to the next question? Anybody who wants to give answers to this? No? Okay. Yeah. So next question. What do you think would be the next groundbreaking result in quantum information science and technology? Don't be shy to be the first person to answer the question if you feel like it. No?
Okay. So I'm an experimentalist. So from my point of view, from probably a very good quantum memory and then you can do the quantum repeater.
So would I come from NV Center or come from?
I don't know.
Okay.
You cannot tell now. But I think quantum repeater seems easier compared to a quantum computer, and all quantum simulator. Yeah, quantum computer seems a little bit. But yeah, quantum simulator also belongs to quantum computer in that sense.
Okay.
So universal quantum computer seems a little bit later, but I think yeah.
So quantum memory. So why is it going to be groundbreaking?
Because there are very recent good results. Cold atom get about around 1 second, and the ion trap already go to minutes, and in some Australian people they get about I think about 20 hours, something like that. But of course, it's not go to single fold level.
So what will be the first application that would be enabled by
Quantum
this
repeater,
groundbreaking?
quantum repeater, and of course, I think overall, I think QKD, yeah, QKD definitely will be the first kind of useful thing for quantum information. Yeah.
Quantum cryptography will move to the next stage once this memory breakthrough has taken place.
I don't see so because I think satellite works and also the metropolitan works as long as you trust the transfer relay. We do not need quantum repeater, but quantum repeater probably is better, but still it depends on what kind of security you want and how much do you want to pay.
But we can remove the trust on the relays if we have a good memory, and that's very critical.
I don't know. Sometimes I don't know whether the country want to control the repeater or not. Not only China, also US, also Europe. They really want to control the center or not. You really want some security by single person? I don't know.
Okay.
I'm not sure about that.
Right. Okay.
Yeah. It's as long as you kind of you trust your government in US. I don't. Maybe not. Not quite sure.
Okay. Let's stay away from politics. Right. What other groundbreaking results you see in the near future?
So personally, I don't think this is a good question because if you can predict, then I don't think it will be a groundbreaking thing, right? It will be engineering progress.
Okay, that's an interesting opinion. All right.
Yeah, I agree with Zheng Feng. Actually, from the quantum software perspective, I would say an important thing is to build a chain of tools.
Okay.
So it cannot be describing as the groundbreaking, but it's the indispensable for the applications of quantum computing.
Okay, so maybe I should change the word groundbreaking, just a very significant development.
Yeah, it's crucial,
it's
but
critical components.
Yeah. So
critical progress.
right.
Okay, I changed my question already. Okay. What will be the next critical progress that will take place?
Well, I see two things that could be very important.
Okay.
I'm not sure if any of them happens, but I think them happening would be very important. The first one would be more exponential advantages for problems in conventional computing beyond factoring to enable more applications that don't do with just quantum simulations.
So people have tried, right? Is there any obvious candidate that people can work on?
There's no obvious candidate,
Okay.
so that's the issue why I don't predict.
Right.
Predict.
Okay. Okay.
And then the second thing that would be extremely important, but also seems to be extremely difficult, would be quantum error correction with lower overheads.
Okay, excellent. All right.
Yeah, and I guess maybe a third one would be something like people call it. I don't quite like the word quantum supremacy, which would mean that you show some example, not a practical example, but something that you can run on your quantum computer with your 70 qubits that seems to be very hard to simulate classically or to even compute classically.
Excellent. There's obvious a race for that.
So that will be
Okay.
also a very interesting next step.
Okay, great.
But again, it's hard to predict when that will happen.
Well, Google said that they are going to do it within a year, right? Maybe within less than a year.
Sure.
Yeah. Okay, let's wait and see. Okay.
No comment.
Okay. Any more to add? Mario.
What I would like to see is a reliable model for the coherence and like quantum error correcting codes or some method which finds that to convince all quantum skeptics that quantum computer can be built. We have such models, and like Peter Shor has shown that, well, for certain model of noise, the current quantum error correcting codes can lead us to quantum computers. But we would need something even more like closer to physics, like a noise model really close to physics, and then a resolution which will completely convince us that quantum computers can be built.
Okay, so there are always going to be skeptics. And I remember in Damian's talk, the story about your advisor talking in a high-performance computing conference, right? Maybe the best way to respond to the skeptics is to build one.
That's right. They say the trial of the cake is eating it. And I think that's true.
Okay. Chang? Anybody want to add to that, the question? No? Okay. So everybody fails. And as a community, we might fail. So let me define what failure is, just to make sure the discussion is more concrete. I would define failure of quantum computing to be within 30 years, we cannot have large-scale quantum computer. Large-scale, let's say factor RSA. Within 50 years. It's 50 years. 50 years we cannot factor our 1024 bits RSA number. Now, could we fail? And if we fail, what could be the reasons?
Well, of course, there's always the possibility that we might fail.
Right.
So if I imagine that in 50 years we cannot build a quantum computer, the question is, do we think that in another 20 years we can build it? Or do we figure out that we have missed something in physics which would prevent us from building large-scale quantum computers? And that wouldn't be a failure. That would be actually really, really interesting. I'm a physicist, so it would be really interesting to understand what limits us in building a large-scale quantum computer. And this will give us a better understanding of what Mario said, like decoherence.
Okay, so possibly some fundamental physical principle prevents us from doing that.
Can always happen.
Okay,
we only
good.
know when we build it.
Right. Possible reason. Any other reasons? Harry?
Well, now I'm optimistic.
Okay.
I don't think we will fail.
Okay, good.
I mean, it could be that we will not have a quantum computer that factors RSA in 20 years from now. That could very well happen. But I think other things will come out of this enterprise anyhow. We have already seen some interesting phenomenon coming out of this, like quantum cryptography, for example, is something that is doable, and these repeaters, they will happen. I mean, it's difficult, but I think it's purely a technological problem. Yeah.
Let me restrict to quantum computing. I know quantum crypto is really...
But I mean, that's something beautiful that came out of this that actually we already know exists. And I predict other things will come out of quantum computing enterprise in the next few years, and certainly within the next 20 years. And one thing that I truly believe will come out for sure is a better understanding of classical algorithms. I already talked about it a little bit.
Right.
And I think that by just thinking with a quantum hat on, we will understand the nature and, in particular, also classical computing better than we do now. So I don't think we will fail. And actually, one way of thinking of it is like you have a big block, massive block of stone that you're trying to open up to chisel, and when you hit a big problem and with a lot of force, always little things will fall off. Little interesting things will come of this enterprise. So I don't think we will fail, and I agree with Damien that it might be that physics prevents us from building a large quantum computer, and that would not at all be failure, right? That would be a lot of progress because now we understand nature better. So
Okay.
I'm
Good.
not at all worried about failure.
I like the-
I don't think we should be.
I like the spirit of turning failure into success. Okay, Ming Sheng.
I want to point to this. Even we are success in the quantum hardware, still we have the possibility to fail in the software because we target not the proper applications. Think about the history of AI. So AI, actually failed in the 1990s. Even the department of AI at the University of Edinburgh was cut. So still we have this.
So what was the reason that it was cut? Sorry.
Because they target, not. I mean, they target the long applications. Because I mean, at this moment, deep learning is so successful. So I always think why this deep learning became so successful. I had been working on AI for quite a while, but it's the old-fashioned AI, logic AI.
Right.
So logic AI is failed because they target the deep AI. I would say, the artificial intelligence. I mean, the intelligence have shallow intelligence and the deep intelligence. But logic AI target the deep intelligence. Machine learning target the shallow intelligence. So shallow intelligence has more applications.
Okay.
In particular in daily life.
Okay, so I understood AI failed in the past because it was aiming at something that's unrealistic at that time.
Right.
Now, coming back to quantum, can you explain again what is the analogy here?
Oh, actually, I have no idea quantum, how quantum can help. I mean, though I'm not working on a quantum artificial intelligence.
But your original answer for my question is maybe the software, we don't do a good work on software, and as a result, we fail to deliver a big application.
Right. So what kind of applications we target?
Okay, great. Okay, Mario.
So I would like to bring up a completely different perspective, which actually a philosopher friend of mine pointed out, that maybe we are super successful as a scientific community to realize like everything we want, but if we fail to convince the public that quantum is safe and it's good, then we have failed. So that's, I think, our task, to teach the public about quantum and to communicate what it is and what it is doing.
That's an excellent point. Basically, you're saying that we could fail not because of any fundamental physical principle prevents us from doing it, but because of societal or policy implications.
Yeah, exactly.
And it could be the failure of our community in communicating with the public, with the politicians.
Exactly.
Now that brings up the following question. Is quantum computing a hype now? Are we doing too much of PR, too much of promise? So that are we raising expectations too high so that we are risking a miserable failure as you described?
Okay, I think Harry.
Well, there's this risk. Of course, there's the risk that it's hyped too much, and certainly some people hype it too much, like it's a wonder machine, a wonder box that solves world hunger and all kinds of problems. And we all know very well that that's not the case. Certainly not anytime soon. And also, usually these problems are not really related so much to computation, but to other economics and political problems. So yes, there certainly is a danger of overhyping quantum computing, and it has been done, and we should be damn sure that we don't do it. And I guess, I mean, that's also, it's just not the fear, but it's a very good follow-up question, but also the overhype that at some point people are tired of us saying that we will have this quantum computer in 5 years, and it's still not there. So we should be very careful in managing expectations of the general public, and I guess also the people funding us. And another thing that's extremely important is that we need more people to work in this field.
Right.
I mean, there's not enough people who work in it at the moment, and there's so many questions, and we need the bright people that I guess are also around here to help us tackle both the hardware and the software problems that are around.
Excellent. Zhengfeng.
I want to add something to the attraction of talent to our field. So personally, I feel that internationally the community is really healthy and really strong and really proud to be a part of the community. And I guess and Alibaba has Yao Yun now, and it's really an exciting move that we have seen industries in China who invest in quantum computing. But if you look at also that from all the FIS departments are really strong. We have USTC, and we have Tsinghua and Zhejiang University, for example, and many others. They are really good physicists who are doing quantum information science. But the point is, if you look at the computer science department, it's really left behind, and it will be a problem for you because you want to recruit at least part of your employees as a computer scientist. And I think there's a big problem, and we have to think about how we deal with this.
Excellent. Yep. It's the same question that the United States faces. So I had it.
But the students is much better, right? You have MIT, you have Berkeley, you have Caltech, you have Maryland. But
definitely. Yes.
Yeah.
Yep.
And CWA, of course, in Europe and many other places.
Great.
What do we have?
Excellent. That's an excellent point. Actually, any more to add to my question? Okay. Or sure. Let's move on to the last question, and it's continuing Harry and Zhengfeng's comments. So we have not just you, scientists here, we also have a room full of people here, and they may be students, and they may be engineers, but they come here for a common reason. They're curious about quantum computing, quantum information technology. What would be your one-sentence suggestion to the students and one-sentence suggestion to engineers? So, okay, 2 sentences for each one of you. The students, let's assume they are in a PhD program for quantum information. And engineers, let's assume that they are just curious about this subject, but they are master programmers, master engineers, but they know very little about quantum information. Okay, 2 sentences, and I hope that everyone can contribute on this question. Chang.
Because I need to go, because I need to catch up my tree. I don't know the panel discussion now. I didn't expect that. But anyway, I give 2 sentences. First one is for the, first sentence will be don't expect too much. And the second sentence for engineering is impossible is nothing. It's a lot like, when I first entered USTC to do my PhD, it's like, okay, it's many flashy experiments, quantum teleportation and the Shor algorithm. It's about 1997. Oh, it's cool. It's very cool. And then I expect a lot of things. I expect quantum computer happens in the 2000. But when I finished my PhD, 2005, then I found it's very slow. So I'm doing the 6-photon, 5-photon entanglement with Jianwei Pan. I'm a PhD. And we use about 3 or 4 years, we get 1 qubit more. So that time I'm very disappointed. I think, okay, probably quantum computer cannot, 50 qubit, 100 qubit, you cannot achieve for my life. But it's amazing, just very recently, now people claim they can get 50, and I think they can. In 5 years. So first of all, don't expect too much because science...
I guess what you mean is be patient.
Science has its rules, sometimes slow, sometimes steep and slow. So I don't know, for this area, I think now we are in the very good area, not technology this way, but I don't know when they will stop.
Okay.
For personal opinion, there is no basic principle say that you couldn't get a very good quantum computer for the correct RSA 1024. So yeah, don't expect too much, but for our engineer, just push it. But I'm not a quantum computer scientist. But for quantum communication side, I think Jianwei told me that he want to do the quantum satellite. At that time of 2005, I think he must be insane. But now it works. See?
Excellent.
So I think quantum computer, I don't know, just try. Yeah.
Okay,
That's all.
Good. So I forgot what you said to the engineers. What did you say to the engineers? For the
Impossible is nothing.
Impossible is nothing.
Yeah, just try.
Just try.
Push it.
Okay.
Push the limit.
That's
what you can
nothing
do.
is impossible.
Okay,
Okay. Good. Excellent.
Just push it.
Yeah,
push it.
Follow your passion.
Push
Okay.
the limit. Yeah.
Okay. Great. Zhang Feng.
I want to start first because otherwise my ideas
Thank you.
may be stolen. Right? So to students, I want to say that it's time to start learning this. Start with either in computer science or physics to learn quantum information technologies. And to engineers, I think it's not very difficult to actually understand the basics of quantum information processing. You do need to learn some sort of a new language, but as long as we have preliminary preparing in like linear algebra, it shouldn't be a big problem. So don't be scared of quantum computing.
Okay.
Can I say?
Yeah.
I guess just
Sorry. Okay. So
go ahead.
You might steal it.
okay.
I think
Harry.
the sentences I would say are, the quantum revolution is now,
Good.
and you all should join it.
Okay.
Or stay home forever. That's what I would say.
Excellent. Good.
Yeah. What I want to say is if you are really curious, talk to the experts and you will definitely learn. That's my sentence, but I want to give an example. I would say where Shilin is. So I had a computer science student working with me. He told me that his physics exam, he got 0 in it. And now he's operating this NMR cloud queue. And he learned to do experiment. So all possible for talents. You just talk to the experts, you will learn.
Okay. Great.
Well,
Damien?
hard question. What should I say to students? I'm still a
You're a
student.
student.
So I think, the only thing I'll say is it's a lot of fun.
Great.
To the second group of people, you mentioned great engineers and other people which are maybe not yet working in quantum information science. I think just join it, because no one has a perfect background in quantum information. I come from a physics background, other come from a computer science background, and everyone can contribute from what he already knows.
Okay. Just do it. Yeah. Okay. Mario?
Well, my students are already enthusiastic. I even did not have to say, but somehow it's in the air. So my
Say nothing.
students just organized like a seminar about quantum without me interfering at all. So I'm sitting in and learning. They are discussing papers and very enthusiastic.
Good. And for engineers?
To engineers, well, catch up.
Okay. Andris?
I have 2 or 3 sentences that apply to both categories.
Okay.
So the first sentence is, quantum computing needs more computer scientists.
Okay.
The second thing is, you can learn quantum computing without knowing quantum physics. I'm actually an example of that.
Me too, actually, yeah. I only have high school physics education.
And yeah, it's simpler than it seems to be.
Great. I think Mingsheng is the last one who hasn't answered. Yeah.
I just have one sentence to say. So start as early as possible. Definitely not after your PhD. Because I have some, I recruited some postdoc research fellow. He has no background in quantum computing, but not. At least at this moment, not very successful. Anyway, of course, always we have some exception.
So, okay, it's
but
hard.
Anyway, we need to start
hard.
as early as possible.
Okay, excellent. You could. Okay, I'll put it in. All right. We have, I think maybe 10 to 15. We have 15 minutes for the audience to ask questions. And I'm going to ask someone to help me to pass around the microphone. Okay. Yeah, it's okay. You feel free to speak Chinese, and I'll try to translate.
我其实对量子不是特别了解，对量子比较有兴趣，所以过来听一听。然后，但我不知道，就是说我们的传统的经典计算机，它跑的是电子，我不知道就量子就是一个电子的一个基本，它应该是一个基本的一个单元。我不知道就是说未来会不会出现，就像我们的经典的计算机一样的，有这种专门的生产量子的那个 CPU 的，然后内存的。刚刚那个嘉宾也讲过，就是说未来的可能一个最大的突破会在量子内存上有大的突破。但我如果按经典的那种计算来说
Try to make your question short so that I remember what you said and can translate.
Sorry.
So it's okay. So what I heard so far is this. So computers we use now are electronic, right? And is quantum computer going to be like that? And so now the computer the industry, we have specialized companies selling memories and some selling chips. Are we going to see specialization in selling quantum memory, quantum processor? Okay.
I think the thing is that the classical computing industry is very successful because we have made the digital computers work extremely reliably.
Right.
Nobody's operating analog computers nowadays, back to my school time I played with them. The problem with quantum computing is that we have a lot of prototypes or small system of quantum computers, but they are all analog. We don't know how to make a digital quantum computer yet. There are two ways. Number one, error correction. Number two, make it topological. Those are what we know. However, we're not there yet. So I really don't know in the future, because if you really want something reliable to use, that has to be digitized. But we don't have that yet.
Okay.
So
Too early to
say.
Okay.
Yeah.
Great. Any other perspectives? Andris?
Yeah, I think we are at the same stage as people were with the first computers, where one party is making everything. So if our field becomes successful, we'll probably end up with same type of specialization that exists in classical computing.
Okay. All right. Excellent. Okay. Next question.
我说中文啊，大家好。
Actually, I encourage people to speak English. Just speak slowly.
我可能会说3个东西，但是我都会很简短的说。第一个就是说，我觉得现在可能提量子计算机啊，可能有点早。我是做计算机专业的，我有10几年工作经验了。我就觉得可能现在量子计算机应该还属于加速卡的阶段。
你说提的意思是，因为我们讨论未来的
就是说我的意思就是说，
我们没有人说我们已经有量子计算机，我们是未来。
我的意思就是说，这个方向就是说，你们定的50年也好，30年也好，可能我觉得有点太虚了。就是说现在首先你要实现1024 bit 对吧？那你又没实现1+1等于2的。
我们有讨论的问题，我们只是I don't think there's any contradiction. Yeah.
然后就是从图灵机的角度来讲的话，就是说，如果你是计算机的话，你必须要是可以模拟别的系统，比如说可以模拟 CPU。但现在我觉得可能量子将来应该是一个加速的功能，它不是说是一个通用的计算机。
So I think this is more a comment. I think this gentleman he felt that we shouldn't be talking about quantum computer. It should be more like a even more basic computing device. And I think I should clarify that. Of course, a lot of talks here are very focused on very narrow, in a sense, on processor and devices. And when we talk about quantum computers, we are talking about vision, right, in the future. Right. So, good. Thank you for your comments. There's a question over there, or maybe comments. Okay.
So I have 2 questions. One is for Yaoyun actually. So do you have any plan for the hardware in Ali?
Yeah, we do have plan. The plan is to work with experimental groups.
Okay.
Yeah. Okay.
Okay. The other question is actually now I know there's a lot of research about the narrow network and manifold physics. So is it like, will it be like a new direction for the quantum algorithm or quantum simulation? Is there like...
Okay, so the question is, there has been a lot of work on neural network.
Yeah, neural network.
And I missed the second part.
And many-body physics.
Medical.
Many-body physics.
Oh, many-body physics. Okay. Okay, so I think we have some experts here. Come in? Okay.
Of course, currently there is, I think when I look at papers coming up, there is a lot of papers on all kinds of different fields where you want to employ quantum algorithm. I think my perspective is what is important currently is focus on the tiniest small problem you can solve. And I think that's where we will do first our efforts, or where I think our efforts should go. So we want to not solve some practical problem, for example, but we want to understand smaller toy problems. That's what physics is all about. And so that's the first thing I think we should be working on. And the rest will then come naturally.
And based on what you said earlier, so that toy problem could be from simulation of physics.
That can just be some spin model we don't understand.
Okay.
We want to simulate some time. It doesn't bring much out of it yet, but it shows that we can, we have small examples.
Excellent. Okay, any more to add? No? Okay.
我们如何开始？因为目前量子计算机还是一个就是非常早期一个概念阶段。如果我们要学习的话，还是用经典的那个计算机来模拟，是吧？就类似虚拟机的模拟，然后做一些简单的1+1等于2的算法。当你说学习的时候，你的意思是说你在自己去学，还是说 in what sense？
就是
去学习这个过程，就了解它的一些原理。
Okay. So the question is, quantum computers are still very primitive. So if we want to learn quantum computing, shall we start with the simulator? Yes.
I think you don't have to simulate. You have small-scale devices online already. Like Bei has in her talk has tell you there's a website you can.
Ali also has this.
Yeah, Ali has also has this plan, and also IBM has this IBM experience. But first, you would have to learn some of the basics to understand what you are doing. Then you can actually have a hands-on experience on what our quantum computing would look like, and you can write programs line by line and get results. That's so it's not about simulation. It's on real device.
I guess there are currently there are many good online courses, like one by Umeshwarani, the other by Actron, and there are many other things offered online. You could just simply take them, so you understand the very basics.
And there's also a standard textbook, Nielsen and Chuang. Okay, any more questions? I encourage people to practice English.
Okay, thank you. From these days, I know that quantum computer needs a lot of fields and expertise from different backgrounds, like engineering or theorist or physics. I'm wondering how industry companies like Alibaba or other groups to cooperate more efficiently, and how you as the director of this plan of Alibaba to break the obstacles or make us to communicate more. Does you have any exact plan in the future?
So the question is actually for me.
Yeah.
Oh, okay. The question is it's also for other people, right?
Yeah.
Let me try to understand. The question is, making quantum computers requires expertise from many disciplines, and how can a company like Alibaba get all those experts from different areas, and how would I communicate with current engineers to help them join us in this effort?
Yeah, because I know that no one knows exactly the whole picture,
right?
And how to make detailed plans to let us learn more from each other and take each other's strengths.
Yeah, I think I have a simple answer.
Thank you.
Can you help me figure out? Meaning that I want to ask people.
I think this Yunqi summit is very great because
great.
we can meet
Great.
a lot of people, and the collaborator laboratories is also very great.
Right.
But how to make the field experts from companies like Alibaba or other companies, because they also they on one hand they are very curious about what computer is, what quantum computer is, and on the other side they may have what they are very good at, and they may contribute more about this field.
All right, so I think Alibaba is a very broad company. We have a very broad spectrum of business. We even have songwriters and singers. So now if we have songwriters and singers, I don't think it's impossible you have engineers or scientists from various disciplines, right? So don't be surprised if you run into a string theorist or a person working on gravity and quantum information. So we are recruiting all kind of people who share our passion and who have the expertise. And for our current engineers, again, this event is an example of we are trying to communicate with Alibaba's employees and also potential future employees. And I also talk to a lot of people, and I give seminars within Alibaba, and I will encourage my future group members to do that as well. But most important thing is, if you share our passion, just talk to me and talk to my group members.
Okay, thank you.
Any other?
Yeah, I have something. I have two comments about the question how to tackle the multidisciplinarity in the field. It is a difficult problem in the sense that it requires time. So we need to talk to each other. And the only way to do that is to bring these people together and let them work on a problem. I guess it's very important that you're not afraid to say that you don't know. When you talk to someone from the other field, something may seem obvious for them and you may never have heard of it. And so you should say, I have no idea what you're talking about. And then they will explain it to you. And this is the way you can go forward. So don't be afraid and talk to other people and encounter on joint projects. And then second remark that popped into my head is that you don't have to know everything. Like in order to drive a car, for example, you don't have to know exactly how everything works. You just need to know some basic things, and then you can drive your car. And the same thing is going to be true in our field. So you don't have to know everything. You have to know some things, and then you can work on it. So don't be afraid, and you don't have to know everything.
Okay. Thank you. So I want to echo that first point of don't be afraid. And I'm going to use Mario as an example. And the point I make is stay curious and let your intellectual curiosity drive you. And I've known Mario for a long time. And one thing that impressed me a lot, Mario has been working on many different areas. And I have witnessed him as a theoretical computer scientist, and then now he's going very deep into physics. And I can see that you are driven by your intellectual curiosity. And I want to encourage everybody to follow my role model and just let your curiosity drive you and let your passion drive you. All right, so maybe that's the right time to end this fantastic workshop. I think maybe we still have some time for the speakers to stay. Maybe I will take two last questions. Okay, two last questions. And I saw this hand first. So I'm going to give this lady the opportunity. And then there's another hand over, who did you see, Harry, earlier?
No, I saw there.
Okay. Okay. Okay, sure. Okay. Okay. You mean how much does it cost? Okay. All right. Are you from a business side? Or? What is the thing? Angel particle. All right. So first question, you all got it. How much will the first quantum computer cost?
It will be free.
Okay, Harry. Let's wish Harry is going to have the first quantum computer. It's going to be free. From other people from Alibaba, it's free. Yes, free too. Yeah. Okay. Second question: what's the relationship between quantum computing and angel particle? This is beyond my knowledge. Next person. Who is the physicist here? All right, Chang. No, Chang is gone.
I think it's just angel particle is related to something approach that is called topological quantum computing. So that is for that field, Microsoft is taking the lead, and the reality is we don't have a single topological quantum bit yet, so it's on the way.
Okay. One last question. All right, please.
Okay. Quantum computer, as we all know, that is very powerful based on superposition and entanglement, but it is very hard to design the algorithm. So I want to ask a question: that is there any other ways to use this quantum power except the quantum computer?
Is there any way to use quantum
effect.
power,
Yeah.
quantum effect, in addition to different from computing?
Yes.
Okay, great. But cryptography is one example. And other than that, that's obvious answer. But okay, no, I already said my answer. Okay, so it's your turn.
Maybe also metrology. Like,
Metrology,
sensing.
Precision measurement and sensing.
Yeah, so and one interesting thing about sensing is that often things that we work out for quantum computers actually turn out to be useful. So for example, there is these proposals to use quantum error correction for better metrology. So things that we designed for quantum computers sometimes turn out to be useful even before we have quantum computers.
Excellent. All right, it's about time. I'm sorry, I already promised. The speakers are going to stay here for a little bit more, so feel free to approach them and talk to them. And let's give a loud round of applause to our speakers. And to you, thank you very much for coming.
Yes, thank you for